So, welcome to the first session of the Extremal and Probabilistic Combinatorics webinar, which is organized by Jan Hladký, Jan Volec-Helena Jepremian, I hope I didn't mess too much, and myself. We will aim to have a session regularly every Monday. Okay, on the screen, you can see our webpage, which I invite you to visit if you haven't done so already. You can find the program with the Zoom link. You can directly click. There is also the link to the slides of the speaker. Also, a little bit below here, there is a link to our calendar, which you can add to your own Google Calendar on the right bottom corner, which is actually, it should display the time of the session according to your own time zone, which can be useful, especially now that daylight saving, there is change of time. There is also information where to write if you want to be added to the mailing list. Also a link to the combinatorics lecture online that is managed by Jacob Fox and Paul Seymour. And we'll add a link to previous seminars when there will be previous seminars with their respective video. Our webinars will be recorded and made publicly available later via YouTube. Hopefully you had information dialogue that have popped up to tell you so, if it worked. If you don't want to be recorded, just don't ask any question during the recording. If you have questions, just raise your hand, which you can do by pressing the corresponding button on the bottom of your screen. And you will be given the possibility to unmute yourself and raise your question. If you prefer not to be recorded, you can also use the chat option to ask your questions. Please use a chat to the panelists and attending option, and you can find the corresponding button also on the bottom of your screen. There will be, of course, a standard question session at the end of the seminar. And also after the standard question session, there will be also a possibility to ask questions without being recorded. We shall try to simulate the informal discussion part of regular seminars. So after the final question session, the recording will just stop, and who wants can join this informal session. So now it's my great pleasure to give the words to our first speaker, Rob Morris from IMPA in Rio, who will be talking about asymmetric containers and additive combinatorics. Welcome.
Nice. Okay, I hope that worked. So thanks very much, Diana. Thanks very much to the organisers for this the invitation to speak. It's a great pleasure. I'm going to tell you about some work that's been going on the last few years, particularly the last couple of years, on applications of containers in additive combinatorics. This is so joint work with lots of people, as you can see. So I'll say during the talk which bits are with who. So with my students or ex-students, Marcelo Campos, Mauricio Collares, Leticia Mattos, and Victor Souza, and Natasha Morrison, who's a postdoc at IMPA last year or the year before, now in Cambridge. David Saxton, who the time where this work was done was a postdoc, now in industry, and Wojtek Samotij. Okay, so I'm going to try to do quite a lot of things. So hopefully some of these collaborators are in the chat and will be able to answer your questions. But I'll try to go slowly and gently as much as possible. Ooh. So start this lecture of combinatorics, which perhaps lots of you already know about. So a set of integers is sum free if there's no solution x plus y equals z. And so if you're looking at the sum free subsets of 1 up to n, well, you could take the odd numbers, that has half of them, or you could take the second half, that's also a solution. So you can find these things of size, and I've already got a typo in the first slide. That should be big O of 2 to the n over 2. Very good. So you can find subsets of size n over 2. So any subset of those gives you 2 to the n over 2 sum free sets. And Cameron Edish conjectured that the truth was within a constant factor of that. This was proved by also the same typo here by Ben Green and by Sapashenko about just over 15 years ago. So they even determined the correct constant, which is, it takes 2 values depending on whether n is odd or even. So again, this should be a 2 to the n over 2, not 2 to the n. Sorry about that. So their proofs, so somewhat interestingly, both used early versions of the container method. If you don't know about the container method, I'll give a very quick introduction to it later. In just a few slides. So these proofs are very different. So Ben's proof involved Fourier analysis. It was a container theorem for sort of 3 uniform hypergraph, but only in the dense setting. People know about these things. Whereas Sapashenko's was about containers for graphs. And so our starting point, or my starting point with these kind of questions was this generalization of the Green and Sapashenko theorem to sparse sets. So you can see by the same constructions, by taking the odd numbers or taking the second half, taking any subset of size m, then you can find easily n over 2 choose m sum free subsets of 1 up to n of size m. And we showed, so with Alon, Balogh, and Samotij, that this is close to the truth. And in fact, this result is sharp up to this implicit constant factor in the big O, as long as m is bigger than square root m. Okay, so this is some motivation. This is one of the first applications of the container method. So we used an early version of the container method to prove this. So the container method developed out of these investigations. Okay, so that's just a little bit of history. So here's a slightly different question, but closely related. So perhaps you all know the definition of a sumset, A plus B. Around the same time, I'm not sure, I think possibly, well, not sure if this was motivated by Ben's investigations of Cameron Edish, but around the same time he asked, how many sets are there of size k and with a given bound on the sumset? So this was directly motivated by his investigations of random Cayley graphs. So if you're trying to bound, say, the size of the largest independent set in a random Cayley graph, then you immediately run into exactly this question. So then proved various bounds and proved some bounds on the independence number of a random Cayley graph using them. So in the same paper that I just mentioned, so one of the key steps was a result of this form, and this led us to make the following conjecture. So what's a way of constructing lots of sets with small sumset? If you want your sumset to have size at most m, well, one thing you can do is take an arithmetic progression of size m over 2, and then take any subset of size k. And then when you take the sumset, you can't escape the sum of the arithmetic progression with itself, which has size m. Okay, so any subset of an arithmetic progression of size m over 2 will have sumset size at most m. So this gives you at least m over 2 choose k different sets with small sumset. And we conjectured that this was close to the truth as long as, okay, k was not too small compared with n. Otherwise, the number of arithmetic progressions messes you up. You can just shifts mean this is false. And as long as m is not too close to k squared. So it's little o of k squared. I should say, in case there are people from the additive combinatorics community in the audience, then I'm using less than in the probabilistic sense, meaning little o, rather than in the number theory sense of big O. See, it always seemed very strange to me that less than should be bigger than less than.
Question.
Anyway, so here's sorry, you have a question?
Yes, there is a question.
Is it in the chat?
Well, okay, so go on.
No, okay. So I hope that questions can be dealt with most easily in the chat. I hope that some of my my collaborators are here and available to answer questions. If that doesn't work, then though, please let me know. Right. So in order to to attack the combinatorics problem, so in order to prove the theorem that I mentioned on the previous slide, we had to prove a slightly weaker version of this that had it was a little larger by some exponential factor in k. But this seemed like a very natural conjecture. And indeed, when m is big OK, so in the bounded doubling case, then with Ben Green we managed to prove this conjecture a couple of years later. This proof used Fourier analysis, so more precisely Ben's regularity lemma for arithmetic regularity lemma. But only worked in for bounded doubling. To say that this was also motivated by the same problem of bounding the size of the independent set of a random Cayley graph. So using this result and some other lemmas, we managed to prove that if you take a random Cayley graph, then it has independence number the same as in an Edi-Shreni random graph. Okay, but that's bounded doubling. So maybe this is a good step forward. But then a much bigger step forward was taken by Marcelo. So this paper has just appeared. So he improved this big OK to almost k squared, so k squared over log n cubed. So this is the first main result that I want to discuss today. And you might say, okay, so he hasn't quite proved the conjecture, but turns out also the conjecture was false. So this polylog factor, well, maybe log n cubed isn't necessary, but certainly some power of log is necessary. So the construction there is very simple. It's just take a subset of an arithmetic progression, but a slightly smaller one, and then have a few elements that are just allowed to be about completely random. So you take some union of a subset of an arithmetic progression, or just an arithmetic progression, and some random elements. Okay, right. Okay, so how did Marcelo prove this? Well, he used the container method. So before telling you what he did, I'm not sure what proportion of people are familiar with the container method. So I just want to give you a very quick, not at all gentle introduction. So apologies for this. So what is the container method? So let me tell you, to try and keep things simple, just the container lemma for 3 uniform hypergraphs. So this was introduced with Yoshi and Wojtek a few years ago, and independently by Saxton and Thomason. So what does it say? So it's a statement about 3 uniform hypergraphs. So wherever you see there's a delta, we're going to have 3 uniform hypergraph with average degree, whatever, D. And suppose that the edges are reasonably uniformly distributed, meaning that the maximum degree is almost a constant times the average. And this delta 2, which is the maximum degree of a pair of vertices, is the most square root D. Okay, this is some condition that's telling you the edges are not too clumped anywhere. Then you can find a relatively small family of vertex sets. Don't worry too much about exactly what this bound says at the moment, such that the following 2 things hold. The independent sets are covered by these containers. So every independent set is contained in one of the containers. And none of them is too big. So they're all sort of 1 minus delta times everything. Okay. Sorry, so this seems, so for those who haven't seen it before, this will seem like a very weird and abstract statement that doesn't look like it has anything to do with anything. But it turns out that this is quite general, quite powerful. So just to give you, if you haven't seen it before, a couple of quick applications. So if you apply this lemma to the hypergraph that encodes triangles in the complete graph, then you get the follow and iterate a bunch of times. So you iterate that previous lemma a bunch of times, then you can prove a statement like this. So there exists a collection of graphs on n vertices, each of which contains few triangles, little o n cubed triangles. They cover all triangle-free graphs. So every triangle-free graph is contained in one of them, and there's not too many of them. So there's only n to the end of the 3 over 2, which is quite a lot. But the important thing here is that this bound in A is essentially best possible. Okay. And why would you care about such a collection of graphs? Well, it allows you to prove things like this. So I'm cheating very slightly here, so you need a slightly more technical version to prove this, but anyway. Wojtek proved 20 years ago that almost all triangle-free graphs with n vertices and m edges are close to bipartite if m is much bigger than n to the 3 over 2. So close to bipartite means there's a bipartition of the vertex set such that almost all the edges go in between and only very few edges are inside the parts. So if you look from sort of very far away, it looks bipartite. Okay, and this n to the 3 over 2 is also best possible. So this you can do some similar things for, say, instead of triangle-free graphs, sum-free sets, or sets without a 3-term arithmetic progression. And the details are very similar. And I should perhaps say, those who don't know, so there's a version of this for k uniform hypergraphs. So all of this works just as well if you want to avoid a different graph, a fixed graph instead of a triangle, or a k-term arithmetic progression or something like that. Okay, so that was a very quick introduction or reminder about containers. So just to give you some flavor of what I mean when I say containers. So we'll see a couple more examples of this a bit later on. Okay, so this is great, but it doesn't seem to apply to the question that we were interested in. However, not long ago with Wojtek and David, we introduced an asymmetric container lemma. So I'll give you some idea in a minute what that means. So we're motivated by the following question. We're going to prove a similar statement for induced H3 graphs. In order to do this, we needed this. The original version of the container lemma was not enough. We needed some sort of asymmetric version. And we were able to prove such a version and prove this theorem. So if you look at almost all induced C4 free graphs with n vertices and m edges are close to a split graph if m is bigger than this n to the 4 over 3 times some polylog. So what does this mean? Close to a split graph, it means you can partition the vertex set into A and B such that you are sparse inside A and dense inside B. Okay. So if you take an actual split graph, then you have no induced C4s. And it turns out this is sharp up to a polylog factor. Okay. So this time we have this log n to the 4 that probably shouldn't really be there. But you need some polylog factor by a construction of Koyakawa, Kreuter, and Steger. Okay, so this is where asymmetric containers came from. This is why we introduced them. And so when we introduced, we didn't think it had anything to do with additive combinatorics. We weren't thinking about this in the slightest. And so it was a great surprise when Marcelo was able to use this asymmetric container theorem to prove a container theorem for sumsets. So here is his theorem. So let m be not too small, and take a set of integers of size n. So there exists a set of family of containers, but now the containers are a bit more complicated. They're subsets of so you get for each container is a subset of the vertex set and a subset of the sumset of the vertex set. Okay, so it's a pair of sets. Again, not too large, such that for every set with small sumset, so you're bound if the sumset of size at most m, then there's a pair with this property. So this is a container for A. So A is contained in X, and Y is contained in the sumset A plus A. Okay. And so for each container, so either X is small, don't worry about that, or the main thing, there are little o x squared pairs whose sum does not lie in Y. So how do you understand this statement? Well, you should think the following. You think that if you have a set which has small sumset, then there's a container such that A is contained in X. X plus X is sort of similar to Y. Right? There aren't not many of the pairs fall outside Y. So Y is a pretty good approximation for X. And Y is contained in A plus A. Okay? And you can do this without having too many different choices for the pair XY. Only about e to the root m. So perhaps many fewer than you'd expect. Okay, let's just leave this up for a few seconds just so people can take it in. Okay, so if you have small sumset, there's one of this relatively small family of pairs which approximate A in this way. So A is contained in X. X plus X is close to Y, and Y is contained in A plus A. Okay. So how did he prove it? So as I said, this was to me at least extremely surprising, but actually the proof is quite simple. So Marcelo applied the asymmetric container lemma to the following hypergraph. So I've drawn a picture. So our vertex set should be a copy of V and a copy of V plus V. So V is a set of integers. We're looking at a subset A of V and its sumset. We're just assuming some bound on the sumset. It's not too big. Okay. And what we're going to find, what Marcelo finds, is a set X containing A and a set Y contained in A plus A, such that they approximate each other. So x plus x is approximately y. Okay. And so what he looks at is this hypergraph that encodes triple, so a and b in x, and then c, which is a plus b, that's contained in, that's not contained in y. So we're looking at pairs in x, a and b, so a plus a misses y. Now this hypergraph has lots of edges, then we can apply the asymmetric container lemma to this hypergraph and take an extra step without creating too many new containers. And this allows us to shrink x and grow y a bit, and so better approximate a and a plus a. Okay, so for those who are not familiar with the container method, this probably sounds like total nonsense, so I apologize. So this is for people who are familiar with the usual container method, perhaps want to understand how one would use this, this method. And so the asymmetry is in this bound. We have this bound on a plus a. We don't have any similar bound on a. So somehow members of a plus a are more valuable because there's a bound on their number. Okay. Right. So this gives the container theorem, and using the container theorem plus a supersaturation theorem proved by Marcelo, he managed to deduce this the conjecture. So that the number of sets with a small sumset is not much bigger than the trivial lower bound. Just take a subset of an arithmetic progression. So this suggests that perhaps actually maybe most sets with small sumsets are close to a subset of an arithmetic progression. And Marcelo also proved this. So for the same value range of m, the following stronger statement that if the setter size k and the sumset is at most m, there exists an arithmetic progression such that almost all of A is contained in P, and P has size roughly m over 2. Okay. So we have this rough structural result for a small subset. Okay, so this is great, but perhaps something even stronger is true. So for triangle-free graphs, for example, it's telling me that my internet connection is bad, so I hope you can hear me. For triangle-free graphs, one can prove not only that that most triangle-free graphs are close to bipartite, but in fact, if you go slightly denser, slightly larger value of m, it's true that almost all triangle-free graphs are actually bipartite. So is something more precise true here? And the answer turns out to be yes. So this is joint work with Marcelo again, but sorry, this is joint work with Marcelo and so Mauricio Collares, Natasha Morrison, and Victor Souza. So do the following thing. So this is only for smaller doubling values. So we're not going to go as far up as Marcelo did. So let's think of lambda as being constant, and let's look at a typical set with bounded doubling. So with some set size at most lambda times k. Okay, and k should just not be too small, so at least some polylog in n. So we've taken the previous conditions, the conditions of the previous theorems. Right, so I removed this condition k is bigger than log n because it follows from this this m is at most k squared over log n cubed. So we're strengthening the conditions somewhat of Marcelo's theorem. We're going to get a much stronger conclusion. So there exists an arithmetic progression such that A is not almost contained in P, A is actually contained in P, and P is almost as small as it possibly could be. So so it's just a constant bigger than the doubling divided by 2. This is the best you could possibly hope for here by this very simple construction. Take an arithmetic regression and take a random subset. is to get the size of P being lambda K over 2. And so this is within a constant factor where the constant depends on lambda and also on epsilon, where you want this to be true with probability 1 minus epsilon. Okay. And actually, it's even closer to being sharp than it looks, because the bound we prove on C is of the form lambda squared log lambda times log 1 over epsilon. And it turns out you can't do any better than lambda squared log 1 over epsilon. So this is really sharp up to just this constant times log lambda. Okay, so a simple modification of the lower bound gives you this extra lambda squared log 1 over epsilon, and we almost get that. Okay. So how does the proof work? Well, the first part for people who are familiar with these kind of things shouldn't be too surprising. So the first step is to apply Marcelo's theorem on the previous slide to get some rough structure. So the first step is to get almost all look sort of very vaguely like an arithmetic regression. One then typically has to do some work to clean up the structure. So we do this. So we get rid of the points that are very far from the arithmetic progression, and tighten things up a little bit. But this doesn't get us all the way to this constant. So the really interesting thing about this proof is this third step, that once we're not too far from where we want to be, we apply the container theorem again to do the counting to get the precise result. So I don't know of any other applications of containers to this cleaning up procedure. I'd be quite interested to learn if anyone knows of any. And also it seems quite promising that it's worked so well in this case. Maybe this should be tried in other similar situations. I should say, we also use the container theorem a third time, so Marcelo's third time to container theorem to prove a key probabilistic lemma about actually the tail of the distribution of the size of s plus s when you take a random set of integers s. So if you take a random set, subset of an arithmetic progression, you get basically almost everything in the middle, but you miss some stuff near the ends, and we need fairly accurate bounds on the tail of the distribution of this variable, the number of things you miss. And this also follows from the container theorem. So this container theorem looked quite abstract, but it's extremely useful. So every time we got stuck in this proof, then it came to the rescue. So if people are interested in these kind of questions, then I want to highlight and advertise this very beautiful and powerful tool, Marcelo's container theorem. Okay. So yeah, and a question for the audience. I'm very interested if at the end anyone has any examples of cleaning up a structure result using containers. And if people don't know of examples, then I think it'd be a good thing to think about, to try and find some more applications of this method. Okay, so we're now halfway through the talk, slightly more than halfway through the time, and I'm now going to switch topics to a different kind of problem in additive combinatorics, or additive and probabilistic combinatorics, to the relate to random matrices. So it won't necessarily look like a problem additive combinatorics immediately, but it will become clear that it is. And containers will also appear, though in a somewhat different form. So we won't be applying asymmetric containers anymore, but we'll still be using container-like intuition. Okay, so here's some background to start with. Listen, anyone who got lost in the first half, so many apologies, but you can wake up now, and this is a new topic, a new world. Right. So where are we? We've got a random n by n matrix with entries in plus minus 1, and we just choose one uniformly at first. And a beautiful folklore conjecture, so I don't know who to attribute this to, but I mean, perhaps someone knows, is that this, the probability that the determinant of this matrix is 0 is roughly this, which is the probability asymptotically equal to the probability that 2 rows or 2 columns are equal or opposite. Okay, so one way to make the determinant 0 would be just to take 2 rows to be equal, and this conjecture says that's basically the most likely way of doing it. If all the rows are different, then you're much less likely to have determinant 0. Okay, it can be natural, but it's surprisingly difficult. So the first result in this correction is 6. Yep.
I think someone, I assume it's Jose Balogh, said that this conjecture is solved recently.
Is solved? Does he say by who?
The nickname is Joe Bal. I assume it's Yoshi Bal. Maybe we can unmute him and he can say more about that. Yeah. Yoshi, can you try to talk?
Yeah, so Mauricio is already answered the question, and also it will be answered in a few slides. So Tikhonov didn't prove it quite this. Anyway, you'll see in a few slides. So, okay, so the first progress was made by Balogh a long time ago, who used Erdős's solution to the Littlewood-Offord problem to prove that the determinant is at least the probability determinant 0 is little o1. Oops, here we go. And a big step forward was made by Kahn, Combinatorics, and Sumset in the 90s, who proved that the probability is exponentially small. There were some further improvements on the constant and the exponent in the 2000s, so by Tao and Vu, and by Bourgain, Vu, and Woods. And then there was this very big breakthrough by Tikhonov, which I think is what Yoshi was referring to, which is just about a year or so ago, who proved that the probability is 2 to the minus n plus little o n. So the conjecture, the full conjecture, is that this probability is actually asymptotically equal to this value, n squared times 2 to the minus n plus 1. Tikhonov, I mean, it's a really amazing result, and a beautiful proof, but it does have this error of 2 to little o n. And it seems, so we looked into this and tried to improve it, and it seems like really significant new ideas we needed to go from Tikhonov's result to the sharp result. So unless there's some more recent work by Tikhonov I don't know about, then I believe this is the state of the art. So this is both an enormous breakthrough and a really wonderful proof, but it also seems to be still some distance from the full conjecture. Okay. Okay, so we're actually getting interested in the following variant of this question, for which somewhat less is known. So let Mn be a uniformly chosen random symmetric n by n matrix with entries in -1, 1. Okay, so just putting the condition of symmetry on. And the same conjecture, it's very natural to make exactly the same conjecture. Okay, so it still should be the most likely way to have determinant 0 is to have 2 rows or 2 columns the same. Okay, and it seems that this question was first asked by Weiss in the 90s. Can you even show this probability is little o1? So Komlosh had shown in the 60s this result for AN for the non-symmetric matrices. Can you show it for the symmetric matrices? And this turns out to be quite a lot harder. It was only solved by Costello, Tao, and Vu in 2005, who obtained this this polynomial bound. In order to do so, they needed a quadratic Littlewood-Offord inequality. So for those who don't know about the Littlewood-Offord problem, there will be a slide in a minute defining it and giving a little bit of history. Okay. But anyway, so you'll see first here that this is very relevant to the problem we're interested in. Okay, this is improved. So the first polynomial bound, sorry, the first super polynomial bound was obtained by Nguyen. This built on work of Tao and Vu and Nguyen and Vu on inverse Littlewood-Offord theorems. I'll also talk about that in a second, for those who don't know about it. Almost simultaneously, the first exponential type bound was obtained by Verschinin. So this also built on significant earlier work by Rudelson and Verschinin. So each of these steps forward has built on some very serious theoretical breakthroughs on Littlewood-Offord problem or inverse Littlewood-Offord theorems. And then more recently, this is the paper that inspired us to work on this question. Faber and Jane improved this e to the minus n to the c to an e to the minus n to the quarter, more or less, using a more combinatorial approach. So they built on work of Faber, Jane, Liu, and Samotij on the so-called counting problem in inverse Littlewood-Offord theory. Okay, so the point of this was to give a little bit of background, but also to point out that all of these steps have been based on advances to do with the Littlewood-Offord problem. That's also true for us. So we improve this a bit further. So from e to the minus n to the quarter to e to the minus n to the half. This is with Marcelo, Leticia Mattos, and Natasha Morrison. Okay, and our main tool, so connecting it to the first half of the talk, is a sort of container theorem for the inverse Littlewood-Offord problem. So I'll state this in a second. But I'd like to emphasize before that, this is not an application, unlike in the first half of the talk. We're not going to apply any version of the hypergraph container lemma. We're going to prove a sort of container type theorem, but by a totally different method. So we're still going to be inspired by this sort of container-like approach. Okay, it was also inspired by this result of Faber and Jane, so Faber, Jane, Liu, and Samotij, that this thing is really about counting in the Littlewood-Offord setting. Okay, so how are we going to go about proving such a theorem? So let me first remind you about the Littlewood-Offord problem. So let G be an abelian group. So for us, you should just think either the integers or the integers mod p. And take a vector in, say, so z to the n, say. And rho of v is, if you take a uniformly, so randomly choose plus minus ones, and take this sum of ui vi, so take a random sum of plus minus vi's. What's which A gets the most weight? Okay. The Littlewood-Offord introduced this in the context of random polynomials, and they proved this this anti-concentration result that whatever V you take, you can't concentrate too much on any point as long as the support goes to infinity. So the support is just the number of non-zero elements. And in a famously and beautiful proof, Erdős and proof got rid of this log factor using Sperner's theorem. So this bound big O size support to the -2 is sharp just by considering the vector of all ones. If you take the vector of all ones, then you're looking for exactly an anti-chain, and so you get the probability of the middle layer. Okay. There have been lots of further results on this over the decades. So here's some example sharks in Semiradi, Halas. So we will meet this this inequality of Halas again in a couple of minutes. So Halas' result will be very useful to us. And so a result of Franklin Furedi. Okay, so this is the Littlewood-Offord problem. It's about anti-concentration of random sums of a vector. Okay, so what's the inverse Littlewood-Offord problem? So its inverse problem just means stability theorems. So can we say something about the structure of vectors where rho is large? Okay. This was initiated by Tao and Vu in the 2000s in their study of random matrices. So if you take a random vector v, whatever that means, then rho is typically very small. And so Tao and Vu observed that if rho of v is anywhere near its maximum value, then the vectors, the examples are all very structured. Building on their work, Nguyen and Vu proved very precise results for rho bigger than, so only polynomially small. This is all, so they use Freiman's theorems. This is all very intimately connected with classical results in additive combinatorics. I should mention that Rudolphson and Verschinin also proved some very powerful and very general results on this problem. So all of these were motivated by results in random matrices. So what are we going to prove? What is our container inverse Littlewood-Offord theorem? So it says the following. So we're going to work in ZP, so let P be a prime. And we show there exists a family of containers which are just subsets of ZP, and there aren't too many of them. So instead of having all subsets of ZP, we only have roughly P to the log P of them. Okay, so some very small family of subsets of ZP. The following property. So for every vector in ZP to the n, this is for any n, with rho of v at least 4 over P, and support not too small. So don't worry too much about this bound on the support. The key thing to look at is this bound on rho. So in ZP, how small can rho possibly be? Well, if this random sequence of plus minus ones spread things out as evenly as possible, so everything got the same amount of weight, then rho would be 1 over P. Right? It can't be any smaller than 1 over P because you have to put probability 1 over the whole of ZP. So somewhere you must have a point that's probability is 1 over P. We're saying if you're just a constant factor bigger than this, then we can get some kind of structure. Okay? If rho is at least 4 over P. So if you're not completely uniform, then, okay, so this is a little bit technical. So this B of V is the container. So there's a set B of V and a set Y, don't worry about Y for a second. Such that the following holds. Most of V is contained in B. So at least 3/4 of the elements of the coordinates of V are contained in B. This is a bit like in the container method where we nibble away a sort of positive proportion. Here we're nibbling away a big chunk. And B of V is not too large. Now this bound on B of V looks a bit funny, but it's actually essentially best possible. So this is what you would get if you took an arithmetic progression. If you took an arithmetic progression, then the size of the arithmetic progression would be roughly 1 over root n times rho. And that's just because if you do an n-step random walk, you spread out by a factor of about root n. Okay. So there's also, there's one technical thing that I haven't mentioned. So it doesn't say rho of v, it says rho of vy, which is the restriction to the coordinates of y, where y is this funny set that we found. So this will play an extremely important role in the application. So I'll have a picture of the application in a few minutes on the last slide. So you'll see why this y is very important. Okay, But for now, you should just think of this as being, there's this very small family of containers such that if your row is just a little bit bigger than the minimum, then you must be sort of half contained in this container. Okay, and the containers are as small as they can be. Okay, so before seeing an application, let me just tell you a couple of words about the proof. So the proof uses Hallas's inequality that I mentioned on the previous slide. So this is something from that uses Fourier analysis. So we don't need any Fourier analysis. That's all sort of hidden in Hallas's proof. But the containers are defined in a sort of excuse me, Fourier analytic way via something called level sets. So people who know what level sets are. So there's something to do with Fourier analysis. And here's the sort of nice new idea. Again, this is people who sort of know about containers, that that we choose not only the set Y, but also the fingerprint of our containers randomly. This is sort of the nice innovation that gives us this very small family of containers. Okay, so this is a bit of a technical statement, but it's something I want to advertise. I think it's a very flexible and powerful tool. So just to finish, let me try to explain how to apply this container theorem to prove this bound on the determinant, the probability determinant is 0. So, okay, so there's some funny Qn of beta, which I'll talk about more in a second. So what this allows us to do is bound this Qn beta. So what is Qn beta? It's the maximum overall W of the probability there exists of V such that M times V is W and rho of V is not too small. So rho of V should be at least beta, which is for us 4 over P. So as long as, so basically you should think of a V for which rho is smaller than this as being random-like. And V for which rho is bigger than this as being structured. So we're dealing with vectors that have some structure. Okay. So Q says, so we're interested in the probability there exists a structured vector such that M times V is W. We're looking for the maximum of that overall W. And that's what we're bounding, showing that that probability is exponentially small in N. Okay? As long as, and crucially, the prime P is not too big. So it should only be 2 to the root N. And by the previous work of Faber and Jane, and which built on the work of Costello, Tau, and Vu, and of Nguyen, this is enough. So that there's a connection, a linear algebraic connection between the determinant being 0, the probability of the determinant is 0, and this function Qn. So it's a few pages of linear algebra gives you this connection, and so this reduces the problem to this combinatorial question of bounding Qn of beta. And so that's the thing that the container theorem gives us. Okay, so we're going to try to. So I just have 5 minutes and 1 slide left. So I'm going to try to explain to you how you can use this container theorem to prove this lemma. So we're going to prove it using the first moment method. So this is, I mean, as usual with containers, you use the first moment method over the containers, but actually here it's somewhat different. Here we're also going to use the first moment inside the containers. There's not like a normal application of containers. So we're actually going to bound the expected number of vectors with this property for each W. So that's what this says. So here's a picture of the proof of the lemma. So we're going to bound the expected number of vectors, V, such that M times V is W, and the vector is structured. We show it's exponentially small. It is for each W. Okay? So we're working in ZP, and P is just at most 2 to the root N. Okay, so here's our picture. We're interested, we fix some W, and we're fixing some V, which is structured. We're going to try and bound the probability that M times V is W. Okay, M is random. M is a random symmetric matrix. Okay, so how can we bound the probability that M times V is W? Well, we have our container theorem. So we apply our container theorem to V, and we obtain a set, a container B and a set Y, and also a set X, which is going to be the set of I, such that VI is in the container, so that's at least 3/4 of it, but not in Y. So here's a picture of that. So what does it give us? It gives us disjoint sets X and Y, both large, such that in X, we know that the VI is in the container. So we have some bound on the number of choices. Okay. And what are we going to bound? Well, we're going to bound the probability that these rows corresponding to X times V equal the corresponding element of W. But we want things to be independent, so we're actually only going to look at the columns of Y. Okay, so the early column, the columns not in Y, multiply by V to give you something, whatever. But then whatever it gives you, then you need the remainder of the column times Vy to equal the corresponding, well, not quite W anymore, but whatever W has been mapped to. And that's bounded by definition by rho of Vy. And now you see why it was important the size of the container was in terms of rho of Vy, because this probability can beat the number of choices. So the crucial thing with the size of the container, let me go back to it, is that the size of the container, B of V, is much smaller than 1 over rho of Vy. So the expected number of choices for V is little o1. Okay, so the crucial thing, and actually it's important, it's not little o1, but it's at most some polynomial in n. Okay. So this bound that we proved that was tight for an arithmetic progression is actually what you need to make this work. Okay. So by doing this, we can pay for the choices of Vx. So all of the V's that lie in X. So we reveal the rows of X, and we bound the probability. So we reveal the rows of X and the values of Vi with I and X. And we use this, our bound on rho of Vy, so the probability that M of X times Y times Vy is the corresponding thing. We use we use rho of Vy. Okay. So in the first step, we reveal the rows of X. And we use the probability of these things in X working out, and we also sum over choices of what happens in the values of Vi with I and X. And because we reveal the rows of X, we've also revealed the columns of X, because our matrix is symmetric. So we're left in this situation. Everything gray has been revealed, and we're in basically the same situation, but just we're working in Z, where Z is smaller. And then we just iterate, do the same thing again. So we apply the container lemma to Vz. We get disjoint sets X and Y. And we do the same thing. We use the probability that M of X times Y times Vy is whatever it's supposed to be. This is bounded by rho of Vy to the power of the size of X. And this allows us to beat the number of choices for Vi with I and X, because Vi has to be in this container. So we iterate, and we iterate, and we keep going until Z is so small that we don't really care anymore, until it's smaller than root n. Okay, and that's the proof. Okay, so I'll just remind you of this, this theorem again, and I'll stop there. Thanks very much for your attention.
Very much, Rob. Is there any question? No. So
so apparently there's a more recent paper by someone called Ermatov that I am not familiar with. Does anyone have any more information about that? Doesn't appear to be available. Is it on archive? Yoshi, you claim this paper exists. Can you? There's nothing on archive by this person since 2018. Okay. Okay. Yoshi is not. It's not backing up this claim yet. So I can see the chat. So if anyone, if you're muted or something, you can ask a question in the chat.
you can raise your hand also, and we can unmute you.
Aha. So the third question, perhaps I can say that. So I think it's an extremely interesting question to improve both Tikhomirov's result and also to improve our bound. And it seems in either case, then fairly significant new ideas will be needed. So we also sort of observe in our paper that e to the minus root n is a natural threshold, or slightly more precisely, e to the minus root n log n is a natural threshold for this kind of approach. So this kind of first moment approach looks like it runs into a brick wall a little bit beyond the point we get to. So it seems it's something really do something fairly interesting and different to push this all the way to exponential. Similarly, with Tikhomirov's result, then getting all the way from down to this this polynomial times 2 to the minus n also seems to be extremely interesting. So if this paper does exist that Yoshi mentioned, then I'd be very interested to see it. Yoshi has left. Interesting. Okay. So I can't hear you.
Rob, are there any cheap variants of this conjecture? So in the maybe in the general setting or in this symmetric setting, where you wouldn't be putting 2 possible values in these matrices, but 10 possible values, would anything substantial change?
I think if you take elements in sort of ZQ or something, I imagine it would be all the same. We haven't really thought about the question. So I don't want to claim that our method works immediately, but I would very much expect it to work for that sort of setting. If you take something a bit more complicated, like, or I mean, either simple or complicated, depending on your perspective, like Gaussian entries, then I suspect things are very different, and I wouldn't like to, without having thought about it, guess if it's easier or more difficult. It could easily be either. I mean, I think it could easily be easier, but I haven't thought about it. But I mean, certainly there's a vast amount of work done on these problems in random matrices that I don't really claim to be familiar. I mean, I claim to be familiar with only a tiny corner of it. So yes, perhaps someone in the chat who knows more about me can answer that question better.
Thanks.
Thank you, Marcelo has stepped in. I should perhaps say also other sort of directions in which people could take it. So people who are less interested in random matrices and more in the additive questions. Then, so we only looked at sumsets, but there's, I mean, lots of other natural objects that one could ask similar questions about. So sums of more sets or product sets, or ask the same questions in different groups. I should say that Marcelo also proved his counting result in an arbitrary abelian group. The statement is a tiny bit more complicated. So a lot of these things do generalize to abelian groups, but certainly there are still lots of open questions, and I guess lots of open questions for non-abelian groups. Aha, Yoji has Yoji has shared a link. This is very exciting. Not a link.
Okay.
Available online.
Maybe if there is no further question, we can just stop the recording and continue informal discussion.
Yep.
Yep.